Hello, everyone, and welcome back. In the past few lectures, we've taken a slight detour and we've introduced a whole range of new functions. Now, I don't want you to lose sight of what the purpose of all of this is. Remember that we started all the way back with the first few lectures showing how you can use definite integrals to understand problems in analytic geometry. And in particular, you can apply those to physics problems to answer stuff that's coming up in the real world. Now, what we've done with the previous few lectures with introducing new functions is we've helped ourselves to describe more exotic phenomena. For example, we can describe curves using an exponential or a hyperbolic trigonometric function, as opposed to something that's just, say, 2x squared minus x to the 3. But the problem that comes with this now is that the integrals, those definite and indefinite integrals that might arise from our early work, become significantly more complicated. They could involve exponential or logarithmic functions or mixtures of the two, sinusoidal functions, all kinds of problematic functions that are not immediately easy to take antiderivatives of. And so this is going to necessitate us to take a deeper dive into antiderivatives, and in particular integrals, in order to see how we can solve these more complicated integrals. Now, we're going to examine one of these techniques today. This is called integration by parts. Now, we've already seen the substitution method, and we saw that substitution undoes the chain rule. Well, in the same way, integration by parts, as we'll see today, undoes the product rule. So let me show you exactly what I mean. Let's remember that if we have two differentiable functions, I'm going to call them u and v today because this is the standard notation for integration by parts. The product rule tells us the following. So we have the product rule. It says that if I take the derivative of a product, I'll say u of x and v of x. You can use f of x and g of x if you want to. It's just sort of standard notation that people use u and v here. This gives me u prime of x times v of x plus u of x times v prime of x. Okay, what if I wanted to undo that process? Well, the fundamental theorem of calculus tells me I can undo it using an indefinite integral. So then I could say, what about the following? So if I slap an integral around both sides of this equality, I still have equalities. And what you can see from the left-hand side is that the fundamental theorem of calculus tells you that the left-hand side eliminates that derivative here. So essentially what I get is u of x, v of x back, and I can distribute that integral. I can use the linear property of this integral to distribute over to the sum in this way. Okay, so you might be looking at this and thinking to yourself, sure, I agree with you. I don't see why this is going to help me though. But if it turns out that if we rearrange this formula in a very precise manner, it leads us to a method of evaluating indefinite integrals that is extremely helpful. And I'm going to illustrate that with a number of examples. But first of all, let me show you what's called the integration by parts formula. And what you typically do is you take that equation that's above here, and you pull this piece right here, you chuck it over onto the other side of the equal sign. And so the result is that if you have the indefinite integral of a derivative of a function multiplied against another function, this is the same as the original two functions multiplied together minus the indefinite integral of the opposite manipulation in terms of these derivatives. Okay, so why is that going to be helpful? Well, we've seen, and I had this general principle in my head, and we've kind of seen it in action, that I like to think of derivatives as making things simpler. And where that comes from is from polynomials, right? Quadratic goes down to linear, cubic goes down to quadratic, etc., right? So there's sort of a simplification task in here. And what this is saying is that maybe you're given a difficult looking integral on the surface, and you think to yourself, how am I ever going to solve this? Well, if you can identify it using these u and v functions, you might be able to turn it into an indefinite integral that is relatively simple. Okay, I gave you the formula. You still don't believe me. Let's just do some examples. Let me rhyme off some examples for you. Let me show you how this actually can be done. So example, let me give you the first one here. X cos of x. Okay, so the first thing that you're probably going to do if I gave you to this, you would start by saying, okay, I usually when I do integrals, I have to come up with a guess for what the antiderivative should be. Do you have one? Because I don't, right? I have no idea what the antiderivative of this function is. But here's what I could do. I could identify which one of these could take the form of u and which one of these functions could take the form of v. Remember, I have two functions multiplied together in here, x and cos of x. And what I want to do is I want to apply the integration by parts formula, and I want to arrive at an indefinite integral that is easy for me to do. So let me show you how this is done. Let's let u equal, so the way I write these things is I take a little space in the left corner here, and I like to identify what I'm going to call u and what I'm going to call v. Now, the way I look at this is I say there's an x in there that's making things problematic, right? I can take antiderivatives of trigonometric functions such as cosine. That's easy. The thing that's making it hard is an x in there. But the wheels start turning a little bit. And I think to myself, okay, x is a pain, but the derivative of x is not. The derivative of x is just 1. So basically what you want to do is you want to play this game with yourself where you have to try and differentiate away the annoying piece of the integral. So that means that if in this side I have this correspondence, the piece that I want over here is going to be easier, and it's going to involve a derivative that gets rid of the problematic piece. So I am going to call v to be x. And that means that if on this side I have v times u prime, I get cos of x here. Okay, now if I start filling in the gaps here, I get v prime is equal to 1. So life is good. And similarly, I can get u by just finding the antiderivative of u prime, which gives me sine of x. Okay, so let me show you how this actually helps. I get x cos x dx. That is, maybe I'll just write it underneath in green. This is v, and this is u prime, which is the same as u prime times v, just written in a different order. And now I get u times v, so I get x sine of x. That's u and v, minus the indefinite integral of u sine of x times 1 dx. Okay, let me fix that up. Let me write that nicer. The x sine x term doesn't need to be changed. It's already in its final form. It's not going to be taken an antiderivative of anymore. And now I've reduced the problem to finding the antiderivative of sine of x. So in this case, the antiderivative of sine of x is negative cos of x. And so the negatives here are going to cancel each other, leaving me with plus cos of x. And because this was an indefinite integral, we should never forget that last term in here. Okay, so now you're thinking to yourself, well, Jason, you knew what to do, right? So that was easy for you. Okay, let me show you what happens if you do it the wrong way. So just as a little scribble on the bottom, maybe you identify u and v in the opposite manner. So let's say you did u is equal to, you did u prime is equal to x, and that means that v was equal to cos of x. And so v prime is going to give you minus sine of x. And so that means that u prime, regular u here is x squared over 2. So look what's going to happen, right? Your u times v becomes x squared over 2 cos of x. Okay, that's fine. That's not going to do anything. But minus, now you have the integral of v prime u, so minus sine of x times x squared over 2 dx. Okay, so let's think about where this started, right? You started with a linear function x times a trigonometric function. You said that's too hard for me. But now what do you have? You don't have a linear function times a trigonometric function. You've got a quadratic function. So you went up in order. You made it harder. So there's a nice sanity check when you do integration by parts problems. And the sanity check is, did I make it easier or did I make it harder? And so you can see that this was a really, really bad choice here because I made the problem so much harder. In fact, I would have to use integration by parts twice now to get rid of the x squared, which we'll see in a coming example. So there is a sanity check when you're doing this. So if you're working through problems on your own at home and you notice that the integration by parts made things even more difficult, try switching what you defined u and v to be. And you'll see that probably with that different choice, things are a little simpler. Okay, let me show you a fun one. If you think back to when I introduced logarithmic and exponential functions in that video, I gave you derivatives and antiderivatives of exponential functions, but I only gave you derivatives of logarithmic functions. So now I want to show you how to find the antiderivative of the logarithm function. And this one takes a little bit of cleverness, okay? Why does it take a little bit of cleverness? Because there's only one function there. I can't see two things multiplied together. But let's think this out for a moment together. Now, what do I know about the natural logarithm? We talked about it in the previous video with L'Hopital's rule. The natural logarithm differentiates into something that sort of behaves like a polynomial, right? 1 over x. And again, in terms of antiderivatives, 1 over x, not a bad thing. It's not that difficult to work with, right? X to any power is not necessarily a difficult problem. So here's what I want. I want to differentiate the natural logarithm if I'm going to apply integration by parts. That means that v is given by ln of x because I want v prime to be 1 over x. But here's the issue. What else is left in there? Well, nothing really, except the number 1. 1 times anything is itself. So you could say, technically, you could view ln of x as 1 times ln of x. And so that tells you that u would be equal to x, the antiderivative of 1. And so now what I get is x ln x minus, let's see how much nicer this became. Now I do u times v prime, so x times 1 over x dx. Remember, we started with a hard problem. I don't know what the antiderivative of ln x is off the top of my head, so I can't just write it down. But what I did is I identified ln x as 1 times ln x, and then I applied integration by parts, and look what I got down. X ln x, that thing doesn't need to, we don't need to do anything with it. There's no indefinite integral around it. minus the integral of 1 dx. So I turned a very hard indefinite integral of ln x into a very easy indefinite integral x. Sorry, 1, which gives me x. And the nice thing about finding antiderivatives is they come with a sanity check, right? If you're not sure that you got the right answer, take the derivative, right? That's the beautiful thing. We spend a lot of time in calculus learning derivatives. And so I would venture to say that most people are better with derivatives than they are with antiderivatives or integrals. And so you can always check your work when you're doing these integral problems just by taking the derivative. Take the derivative of that thing right there and make sure it's equal to ln of x. It's a nice check. Okay, let me show you another example. So when you see these integration by parts problems a lot is when you have these transcendental functions. So these exponentials or these trigonometric or these hyperbolic trigonometric functions multiplied against, say, a polynomial. And the reason integration by parts is so good with these things is because after enough derivatives, a polynomial just sort of disappears. We saw it, if I go back, we saw it with x times cos of x. You take one derivative, x disappears from the whole equation. So when you see these polynomials multiplied against exponentials, for example, you know that if you take derivatives of exponentials, you just keep getting exponentials back. And so integration by parts probably isn't going to help you with that. But I know that if I take the derivative of x squared, I go down to x. At least I reduce the order. So let me show you how we want to handle this. Let's take, let's use the formula here. So we have u prime times v. So if I have u prime and I have v, then I want to differentiate x squared. So I'm going to call that v. That means that I get e to the x here. And I get u. Again, the antiderivative of e to the x is just e to the x. Nothing too hard there. And now I have 2x. So let's see what this gives me before we keep going. X squared e to the x minus the indefinite integral of, in this case, u times v prime, which is 2x e to the x dx. Okay, so, on the surface, I didn't really help myself because I still don't have an indefinite integral. I don't have an indefinite integral I can just come up with off the top of my head, right? Or even just work through in a simple way. But I did help myself in a little bit because I turned myself from a quadratic function x squared into a linear function x. So let's try it again. Let's use integration by parts again. So let me filter off this term because I just want to solve that definite integral and we'll put everything back together at the end. So now I have 2x e to the x dx. Imagine we started with this. This was the original problem, imagine. Well, I'm going to use integration by parts to get rid of the x term. So I have u prime is equal to e to the x. That tells me v is equal to 2x. That tells me v prime is equal to 2. And it tells me u is equal to e to the x. So applying integration by parts to this integral gives me 2x e to the x minus the indefinite integral of 2 e to the x dx. No more x's, right? So I just needed to use integration by parts twice. And the reason for that is because when I differentiate x squared twice, I get a constant function. So in this case, I get a relatively simple antiderivative, and I get 2 e to the x and then plus c. Putting it all together, so this gives me that the antiderivative of x squared e to the x dx is equal to x squared e to the x minus, now I'll put in what I just solved for. E to the x and then plus c. And now here I get x squared e to the x minus 2x e to the x plus 2 e to the x. And I'm going to write it as plus c again. Again, it's just a constant, so it doesn't really matter. You can write minus c, that's perfectly up to you. The fact that it's not defined, it can just be anything. So I'm just going to write it as plus c again. But that's it, right? So if I ask you, for example, to find the antiderivative of x to the 10 e to the x, you can do it. It's just going to take 10 derivatives to get rid of the x to the 10 term. So that means you have to use integration by parts 10 separate times. So it's, it's like those Russian dolls, right? It keeps cutting out. And then, in the very, very center is the small, easy one. And so then you solve that, and then it goes back to the next biggest one. It solves that, and then it goes back to the next one, and it solves that. And you just get this cascade. So we're not going to do that right here because I want you to try that out on your own, see how it works. Let me give you another example of this, where you take two transcendental functions and you multiply them together. So things get really weird here. This is one of my all-time favorite integrals that you can do. So number 4 is the e to the x cos of x dx. Okay, so both of these are transcendental functions. E to the x differentiates into itself. Cosine differentiates into minus sine. So, we're not going to make things too simple right away. But what we could do is just kind of see what happens. Right? Let me show you what will happen here by picking u and v. And we're going to have to use integration by parts twice again. I'll show you. This is a really, really cool example. It's not obvious, right? And so I want you to just watch what happens here. And then once you see the process, then maybe it'll make a little more sense. So let's say that we have, for example, u prime is equal to, say, cosine. And that means that v is equal to e to the x. So v prime is equal to e to the x. And u is equal to minus sine of x. Okay, so then in this case, there's no minus on the sign. Sine of x. I sometimes get confused with the trigonometric functions going backwards and forwards in differentiation and integration. Okay, so I get e to the x sine x, that's u times v, minus the integral of, in this case now, e to the x sine x dx. So, okay, what have I done so far? Not a whole lot, right? I swapped down a sine for a cosine. So I didn't make myself that much easier. But let's do integration by parts again. And I'm going to do it on this line one more time. Let me write the next integration by parts in green underneath here. So again, I've got u prime and I've got v. I'm going to do exactly the same thing I did before. I'm going to use v is equal to e to the x, and I'm going to use u prime is equal to sine of x. So then this gives me v prime is equal to e to the x, and u is equal to minus cos of x. There's that minus showing up. Okay, so then the whole big indefinite integral, what does it become? Well, I get minus e to the x cos x, and then minus, in the indefinite integral here, you get a minus from the cos x that's going in there. So I'm going to make that a plus, and I get e to the x cos x dx. Okay, before we get too excited, let me expand it out. So I get e to the x sine x plus e to the x cos x minus e to the x cos x dx. Okay, now you're thinking, Jason, that was stupid, right? That was just plain old dumb, because now I'm right back at the same integral that I started with. But check it out. I now have an equality statement. I have the same term on both sides. Let's collect them together. So this actually gives me 2 times the integral of e to the x cos x by taking this one right here and moving it over to the left-hand side. So it becomes positive. So I get 2 of them on the left. Sorry. Sorry. Okay. And then on the right, no more integrals. So I can divide off by 2, and I've solved my integral. So let me show you. 1/2 e to the x sine x plus e to the x cos x. So why did this work, right? Why was it that I arrived back at the same integral again? Well, it comes from the circular nature of trigonometric derivatives, right? Sine goes to cos, cos goes to minus sine goes to minus cos goes back to sine. So for derivatives, these things repeat each other. Every second derivative, they get back to a negative of themselves. So that's why this worked. And this is a cool trick, right? Like I said, it's probably not something you would come up with if you were just doing this on your own. But now you've seen it, it's a really, really cool example. And in fact, this idea can be carried over to get recursive definitions for integrals. So let me show you another example here. Let's find a formula for successive powers of cosine. Okay, so let me, again, this is similar to the natural logarithm example where I kind of just gave you one function. Technically, there's n of them, right? I multiplied cos together n times, but it's written all as one function. So the first thing that I want to do is I want to be able to make this thing actually look proper or look like something I can work with. Okay, so all I did is I took one of the cosines and moved them over. So I separated them out. And the reason I'm going to do that is so I know how I can apply integration by parts here. And so what I'm going to use is I'm going to use, sorry, I'll move this over a little bit so I don't take up too much room. I want u prime to be cos of x because that's the only thing in there that I can find an antiderivative of. And so that means that v is equal to cos of n minus 1, cos to the power of n minus 1. So then this tells me that u is equal to sine of x. That's okay. And v prime is n minus 1. So we're using the chain rule right now. Cos of n minus 2 of x, and then times minus sine of x. So that thing is brutal, right? It's pretty ugly. Let's toss this in though. Let's see what happens. So you know what? You might hate me for it, but in the long run, it's going to look nicer than me trying to cram it in up there. So now my integral becomes cos of n minus 1 of x times sine of x plus, let's pull the constant n minus 1 out front. And now the plus here comes from the minus that should be a dot representing multiplication. But this is a minus sine of x coming from the inner derivative, the cos of x derivative. That's going to make this thing right in here minus minus, so a plus. And what do I have? I've got a sine coming from the u term. I've got a sine coming from the v prime term, sine squared x, and then cos of n minus 2 of x dx. You're thinking to yourself, whoop-de-doo, that didn't help me at all. And first of all, I disagree. I don't think that's the case because I can use the Pythagorean identity to put that integral all in terms of cosines again. We know that sine squared is equal to 1 minus cos squared. And so let's just for a second, let's expand out some math and let's take a look at sort of what's going to happen here. So nothing on the front end is changing because these are just, there's no derivatives associated to them anymore. Now, if we expand out that 1 minus cos squared term into separate integrals, I get cos n minus 2 of x dx plus n minus 1 integral. Sorry, I should have a minus out front coming from the minus cos squared. And I have a cos squared and a cos to the n minus 2. So I get cos of n again, dx. And it's just like what I did last time. I got back at the back end here, I got the original integral that I started with. Remember, I started with cos of n. So this tells me that if I pull this guy onto the left-hand side, I get n minus 1 of this integral plus another one. So that's going to give me n of them in total. So this gives me n integral cos to the power of n of x dx is equal to, now let me write it all out. Integral cos n minus 2 of x dx. And finally, we can divide off the n to get cos of n of x dx is equal to 1 over n. Again, n is just a constant, so it's not really doing much here. It's just a number that's being divided off. Sine of x plus n minus 1 over n, the integral of cos of n minus 2 of x dx. Boom. Okay, so maybe you're not very impressed. But I certainly am, because I was tasked originally with finding the antiderivative of cos to the n. And what I did is I essentially posed it in terms of finding the antiderivative of cos to the n minus 2. This is a recursive formula, kind of like the Fibonacci sequence, where you add the previous 2 to get the next one. This says that you can work up from n. So, for example, let's take n equal to 3. Well, then this gives me that the integral of cos cubed x dx, again, a difficult integral for me to actually find. Well, for my formula, this is 1/3. Maybe I'll start it on the next line just so I can fit it all in. This is 1/3 cos squared x. So I'm just substituting n is equal to 3 everywhere. Plus 2/3 the integral of cos to the power of 1. That's just cos. So this now gives me 1/3 cos squared x sine x plus, now I just have an antiderivative of cosine. So this is 2/3 sine of x plus c. That's it, right? And so now that I've got the integral of cos cubed, now I can find the integral of cos to the 5. Why? Because if I take n equal to 5 here on the left-hand side, from my reduction of order algorithm, it says that it's really just this thing right here. So let me just write it out. I'm not going to simplify it because it's going to be ugly. But this tells me the integral of cos to the 5 of x dx is equal to 1/5 cos to the 4 of x sine of x, and then 4/5, and then the integral of cos cubed, which I just calculated above, so let me just write it all in. Cos squared of x sine of x plus 2/3, sorry, that's bad, sine of x. And then I'll just pop the plus c on the end because that's not really making a difference. But now if you wanted to, you can find the integral of cos to the 7. And you can restart this process using the even numbers as well. You can use it for n equal to 2 if you really want to. And you can just build up from there. And you have your cos of n minus 2 would just be the constant function 1, right? Because that's cos to the power of 0. So you can restart that process again. So that's pretty cool, right? That's a nice recursive formula. If I really wanted to, I could I could program a computer to find cos to the power of 1001, the antiderivative of that, because I could just let the computer run through all of the n's until it gets up to n equal to 1001. I'm not going to do that by hand because that's going to take me a super, super, super long time. Okay, then what I want to close with is I want to talk about definite integrals. Okay, so everything sort of transfers over to definite integrals. So let me give you the formula. So integration by parts formula for definite integrals. This just comes from the fundamental theorem of calculus again. So what you get here is if you want the definite integral of, say, u prime times v, this is u of x times v of x evaluated at the endpoints. So we know this notation, we've seen this, that's evaluating at b subtracted from evaluating at a minus the integral from a to b, and now you just switch the derivatives around. Now, in some sources, they might exchange the roles of u and v. So sometimes you might see u times v prime on the left-hand side. That's totally fine. You can just rename everything, right? So just rename the u's v's and the v's u's. It doesn't matter. The only thing that matters is that one of them is being taken the derivative of and one of them isn't, right? So I just don't want anybody to get confused with maybe if I mixed up notation compared to some other source. Okay, so let's finish it off with a final example. Let's say find the area, let's say, of the region bounded by the curve, sorry. Y is equal to x e to the minus x, and the x-axis from 0 to 4. Okay, so you can sketch that if you want, but in this case, these are both positive or non-negative functions. So it's a relatively simple thing to do. All that we are going to do is find a definite integral. So we're gonna go right into it, and let's calculate. In this case, we're looking for the area of a region. So we can go back to these Riemann sum type arguments, and we can say that this turns into a definite integral. And so we get essentially just this, nothing too special. We don't really need a sketch of it because, this is sort of routine for us now. The only thing that's not routine is that we're going to have to use integration by parts. So what I see is a polynomial multiplied against a transcendental function, an exponential. I know that under derivatives, polynomials disappear. So I want my u prime equal to e to the minus x, because that's going to give me v is equal to x. It tells me that v prime is going to be 1. It disappears under differentiation. And so u is equal to minus e to the minus x. So fairly straightforward. This gives me minus x e to the minus x running from 0 to 4 minus, now that's going to become a plus because of this thing right here. And I get the integral from 0 to 4 of e to the minus x dx. So life is good, right? This is very, very nice. So now, before I evaluate at the endpoints, let's actually do the antiderivative here. This gives me minus e to the minus x. These are definite integrals. There's no more plus c's. So here now, you get minus 4 e to the minus 4 minus, well, I guess it's plus 0 e to the minus 0. So this thing is going to disappear, and then minus e to the minus 4 minus 1. And so you can clean this thing up a little bit. You get 1 minus 5e to the minus 4, which if you want to put that into your calculator, if you really care about what the final answer is, 0.91. But the point is, definite integrals can now be handled in exactly the same way. And it's, of course, antiderivatives help us mostly with definite integrals, at least for what we've seen so far. So it's, of course, the definite integrals that we're most interested in. And this is sort of telling us that it's pretty simple. Things aren't too bad. Okay, so what we've seen today is a way of undoing the product rule. And this leads to what's called integration by parts. Typically, it's the most difficult of the integration rules for students to get their heads around. It usually confuses people, and it's something that takes a lot of practice. But what we've seen from a lot of the examples are that there's ways of using integration by parts to get really cool formulas, especially some of these recursive formulas, or the integral of e to the x times sine of x or cos of x or something like that. Okay, so we'll pick back up in the next video with more techniques.